Okay, so let's take. I want to once again highlight how much better it is to deal with energy arguments than vector arguments. Okay, so let's say that we got a game of catch going on. Somebody throws a ball from ground level over here at 20 meters per second. We don't even need to know the angle. It's going to get up to some maximum height. Let's just say at 15 meters, and then if it comes back down to the ground, somebody catches it. So, in the absence of any air resistance, which we're assuming, how fast is the ball traveling when it's caught?
9.8 meters.
Once again, it gets thrown at a speed of 20 meters per second. It arcs up to some highest point.
20
back.
meters per second.
20 meters per second. Okay, prove it.
Because it doesn't change. It starts with zero kinetic energy, ends with zero.
Okay, so by the work energy theorem, right? How many forces are doing work on the ball? One, right? Gravity is. Agreed? Gravity acts in what direction? Down. Okay, so if gravity's acting down, then if it's traveling from here to here, that's a horizontal displacement, right?
Yeah.
So it hasn't moved anywhere vertically, right?
Yeah.
So there's no net work done by gravity, right? Because the work done by gravity equals FD cosine theta. But traveling from there over to there is at a right angle with the direction of the force of gravity, which always acts
So
vertically
does
down.
it really help us at all with the 15?
Okay, well, so gravity does no net work. Now, it might do some work, like if I were to pick, for example, how much work it had done at that point, that's going to be non-zero, isn't it?
Yeah.
Because at that point, the displacement from there to there, well, there is definitely an angle associated with that, right?
Right.
There's the displacement, here's the direction of gravitational force, and so there's an angle there, right? and so we are going to get a component. We don't even really have to know what the angle is, though, because we know that the vertical component of the displacement was just 15, right? Does that make sense? So the work done by gravity at this point is going to be the force, which is just, we don't even know what the mass is, so it's just mg, right, times 15, but it's going to be negative in this case, because the ball traveled up, but gravity's pushing down, right? Does that make sense? But here, it's zero, because now it hasn't moved at all vertically, so it's going 20 meters per second. Well, the speed is 20. Yeah. Because we're not going to be dealing with energy, we don't deal with vectors, right? We just deal with scalar quantities, which is really nice. Okay? Already you get a sense this is a lot easier to deal with. Okay, I want you to tell me how fast is the object going at the top of its trajectory? So I want to know how fast is it going at this spot right here? How fast?
Zero.
Well, no, it's probably traveling at some speed.
Oh, I mean, not for.
How am I going to know?
Wait, does it start with 20 and 20?
It does.
So isn't it just 20 the whole time?
Well, okay, I can prove to you that it's not by using the principle of exaggeration. What if I threw it more straight up and down, right? So what if the trajectory, this is kind of a cool principle too. This, what you always, if you want to prove something to yourself or somebody else, use the principle of exaggeration. Take any of the properties up here and exploit it to make it real extreme. And oftentimes you can see conceptually that that can't be the answer. So what if the trajectory was like this? Now, wouldn't you agree that at that point right there, it's definitely going slower than it is at the beginning or the end?
Yes.
It's only got just a very small horizontal component of velocity, right?
Yes.
How am I going to figure it out? You can't, by the way. You have the tools to figure it out right now.
Do we use the 15?
Yes, you do. But I didn't tell you anything about any angles here, did I? So you don't have to do this the old-fashioned hard way. There's an easy, elegant trick to this. What do you think? Okay, I can maybe, let me pull you away from that argument, because I can see, and I'm sure this is going on in a lot of people's brains right now, they're thinking, okay, the fact that it's horizontal must have something to do with it. Nothing at all. I could, for example, pick this spot right here, and I could say, well, okay, that's 12 meters, and it's not traveling horizontally, and the question would be just as easy.
12 times 20.
Nope. So at any place where we know the height of this thing, we can calculate, ignoring wind resistance, spray resistance, which we are. Ball's coated in slippery and it's 5 meters per second. How'd you get that?
20 divided by, or no,
Or minus.
No, not quite that simple.
Something a derivative, something?
No.
Isn't a percentage?
Okay, but now think about this in terms of, what do you know about work and energy? I mean, we don't know a ton, but we know enough to probably deal with this. There's a relationship here.
Output,
Okay, but there's no real simple machines here, right?
power?
Okay. Okay, so we do know something, right? We do know that we could calculate what the kinetic energy is here and what it is here, right? We don't know the mass, but we could write it in terms of m at least, right?
Yeah.
Everybody agree? Okay, so the kinetic energy, we'll call this, this is our initial position, so we'll call this k sub 0, and that's equal to 1/2 times m times 20 squared, right? Which is the same thing as 200 m. Okay,
And it's 200 m at the other side.
and it's 200 m right here. Okay, so k final equals 200 m. Okay, I don't know what the kinetic energy equals at the top directly, but I can probably figure it out.
Divide by 30.
No, there's something going on though. What's the relationship between the work due to all forces, or the work done by all forces, and kinetic energy? Well, okay, but that's old school. We don't need to use that. Eventually we're going to be going there. We haven't really. Okay, well, but just somebody tell me, what is the work energy here?
Now work equals.
Okay, so the work done by all forces equals the change in kinetic energy, right? Everybody agree?
Yeah.
How many forces are acting here? One, right? So the net work, or the work done by all forces, is just equal to the work done by gravity, right? So let's take this spot right here, for example. Okay, so at this part right here, the work done by gravity, we already calculated, right? The work done by gravity here is equal to mg times 15 times -1, right? Because it's negative work, right? Does that make sense? Okay, so that's got to equal the change in kinetic energy, doesn't it? Right? So, well, okay, so that's equal to, we know that the work done by all forces equals the change in kinetic energy, right? So in other words, negative 15 mg equals delta k, right? Well, that delta k is just the same thing as the kinetic energy here minus the kinetic energy that we started with, right? Okay, no, not 0. So I'm going to get, call it K1, that's going to be our kinetic energy right there, minus 200 m, right? So I should be able to solve for what the kinetic energy is there, right? Okay, so then that's going to give me K1, if I just add this to the other side, I get 200 m minus 15 mg. Let's just take g to be roughly 10 to make this easy. Agreed? So that's roughly equal to 100 m minus 150 m, if we take g to be 10. So it's roughly equal to 50 m. No, because g, we're going to take g to be about 10, right? Everybody agree? Okay. Well, kinetic energy is 1/2 mv squared, right? So then we can set up an equation. This must just equal 1/2 m, we'll call it V1, call this is position one right there. 1/2 mv1 squared must equal 50 m. Well, now look, this is pretty cool, right? Look what we did.
I'm confused on which lowercase m's are repeaters and which lowercase m's.
There's no units up here at all. M is just mass. Okay. Oh, I guess I did put one, that's a meter. Okay, sorry, that's the only meter, yeah. Other than that, we just should've made it something different. Okay, so then the masses cancel, and that's convenient. And now I can solve, if I multiply each side by 2 to get rid of the 1/2, don't I just get v1 squared equals 100 in standard units? So what's v1? 10. They don't always. I try to think about how they're going to work out. They don't always work out. That one did. That's good. So we get a nice even number 10, right? Okay. But wouldn't you agree that I could have done that anywhere? I could have done that at 12, right? And I would have just gotten a little different answer. It would have been a little bit bigger, wouldn't it? I would have gotten a little bit higher speed, right? Well, so once again, the 15 and the 12 are not special in any way, right? Not special in any way. Those are just numbers I happen to pick. I could have picked 5 or 7.9 or something, and then we could have found out how fast it was going at that height. Okay. So what if we made this a little different then? What if we said, let's do the same picture, same exact picture. Okay, here's the start, here's the end. Here's our light bulb, going up to this spot, down to this spot, right? Let's just say, let's call the height, we could call it 0 if we wanted, that's fine, but let's not. Let's call the initial height of the ball h naught, okay? Just so we're not pinning ourselves down to having it always have to be 0, right? It's just going to be h naught. So at this height, this is at y equals h naught, and this point up here, we're going to call this y equals h. And we're going to give it some initial velocity, which we're going to call v naught. Okay. And we could calculate a velocity up here. Okay. We could do the same problem, couldn't we? Right? There's only one force acting, and it's gravity. And keep in mind that all of the kinetic energy that we lose, gravity gave us back in the end, didn't it? Right? So we mentioned this earlier in our discussion of energy, but what do we call that receptacle for that kinetic energy then? Where is it stored? The gravitational potential energy, right? So gravitational potential energy is just like a gravitational spring that we're loading up and then allowing to unload, right? That's it. That's all it is.
Real quick, what is y equal?
So we're just gonna say that the height of this thing is h naught.
Is that what that is supposed to be?
Yeah. So the initial height is h naught, and the final height is h. Then let's call this h1.
I made it different.
Okay. And so, how much energy when the thing gets up to the top of its trajectory? How much work is being done by gravity? Well, the difference between those heights is just h1 minus h naught, right?
Yeah.
Everybody agree? And so we end up with the work done by gravity is just minus mg h1 minus h naught, right? And that plus its kinetic energy up here must equal what its kinetic energy was down here, right? Because this is the work done by all forces, and that's equal to K1 minus K naught, right?
Equals mg, is it?
And why don't I, instead of calling it K1, let's call these finals. So we'll just deal with just this part, right? So we have our initial and our final, right? So once again, K final minus K naught equals negative mg hf minus h naught. Well, I'll tell you what, let's just define that distance as h. H is just going to be the difference in the heights of the two places. Okay. So let's mix and match a little bit. Let's push this over to this side and this over to this side, right? Maybe flip them around. So on one side we've got K naught by itself. On the other side we've got K final plus MGH. Whoa, that's pretty cool. Right? Okay, think about that. So what that's saying is our initial kinetic energy, some of it was lost, and the part that was lost was stored in this other term called MGH. Right? Yeah, which is our gravitational receptacle, our gravitational potential energy, right? Okay. If we went back and said, okay, well, maybe we do want to talk about this as H naught and H final. That's okay. We could do that, couldn't we? Then we would just say, what would have happened if we would have done that? Then instead of calling this MGH, we would have had, this term would have been minus mg times H final minus H naught. That's okay. Now look where we can go with this. So if I distribute, so that's gone. If I distribute this negative, I'm going to get K final minus K naught equals negative mg H final plus mg H naught. Right? Push this over to this side and this over to this side, and then let's just flip the equations. And you tell me if this is right. It's right, isn't it?
Is that supposed to be the same as the KO, KX of the CH one?
Well, all we did essentially is we just said, okay, let's let the difference in the heights, we'll call it H, which is fine, but we didn't have to. We could have said this is starting at a height of 1 meter and it's ending at a height of 16 meters. That's fine, right? We could have said that this is starting at a height of negative 3 meters and it's ending at a height of 13 meters, right? Or 12 meters. Either way we do it, we're still just getting the same differential between the two, right? It's irrelevant. It doesn't really matter, does it? Either way we look at it, and this is really, does everybody see this? This is really cool. You gotta really think about this for a second. But if we define this H as just being the change in height, does it even matter what we called the initial height or the final height? No. Doesn't matter, right? So this is key. The reference point for measuring the height, the vertical offset of something is completely arbitrary. Completely arbitrary. All that matters in a situation like this is how much is the height changing, right? We could set the height as being, like if we were doing this experiment in here, we could set the height as being the floor when we launch the ball up, right? Or we could set it as the ceiling. Doesn't matter. If we set it as the ceiling, we start off at like negative 3 meters, and maybe it gets up to negative 2 meters, right? Makes no difference. The difference is still 1 meter, right? So what's this telling us? This is pretty key. In the absence of friction, right? Because we said no air resistance, the sum of what two things appears to always be constant. It's not just kinetic energy, though. What do we call this? Gravitational potential, right? So the sum of an object's kinetic energy and gravitational potential energy is constant. Wow. Combined, we call this mechanical energy. Okay, because mechanical energy is just the energy of position or speed. Okay? So mechanical energy is conserved in the system. absent friction.
Okay, can you say it one more time, what MGH stood there?
So MGH, it just stands for, that's just our definition of gravitational potential energy, okay? And once again, the H is totally arbitrary. All we care about is the difference in H, right? So this comes down to something kind of interesting then. We could say that in a closed system, if there's no friction, what do you think is always true for all energy? It's conserved, yeah. In a closed system, energy is conserved. And in our universe, which is the ultimate closed system, even if we account for friction, energy is conserved, right? When friction occurs, energy is just transferred from, like for example, if a object slides to rest, then the kinetic energy of the macroscopic object is just converted into kinetic energy of the little molecules, and it's radiated away as heat. Okay? The universe is going through this process constantly. This is something which you will study physics, which I really hope you do. You will look at this from a completely different perspective in another part of physics called thermodynamics. In thermodynamics, we just study, it seems like thermodynamics is just the study of heat. It sounds like thermal means heat. And a lot of it is. Thermodynamics is the kind of physics that you would study to understand, for example, how a heat engine works. If you want to understand how an internal combustion engine works, well, a lot of the properties of an internal combustion engine are described by thermodynamics. Okay? But beyond that, it's actually, on the surface, that's what it is. But when you study it more completely, all it really is the study of randomness. It's the study of what we call entropy. Entropy is the number of possible states of all particles in the universe that are occupied. It's one way to think about it. So entropy is randomness, right? Randomness always increases. Always increases. There is no, on a systematic scale, there is nothing that ever happens in the universe that reverses entropy. Now you can do this locally. You can freeze ice. And if you freeze ice, think what you're doing. You're taking the potential positions of all these water molecules and you're confining them, right? Instead of the water molecules being able to move around freely inside this little container, they're frozen in place. And so the entropy has decreased. The number of available states those molecules could have has decreased. And what's just absolutely amazing, that still blows my mind even just to think about this stuff, is that sure, you can think about this using a bunch of heat equations, but like the thermodynamics that I eventually ended up studying in college was completely statistical. You almost never even said the word heat. It just had to do with the number of available states of molecules in place. And you get the same answer. And so why is it then, and I'm just touching on some of these a little bit because really, we could have talked about this stuff in here a little bit, but you need to have a lot more math to really understand it. So you'll get there. But if we're decreasing the entropy of that ice, right, we're freezing it and we're confining the molecules to not be able to move around very much. So they've gotten more organized and less disorganized. That means that we have decreased entropy. Not really though. Because in order to freeze them, where did I have to put them?
Absolute zero.
Well, maybe not absolute zero, but I had to probably put them in my freezer at home, right? Think about what I'm doing when I put those in my freezer. My freezer is having to suck heat out of the internal compartment of the freezer and distribute it into the environment. Do you suppose it's perfectly efficient in doing that? No, it's not. It's not perfectly efficient. So it's actually using more energy to extract that energy from the freezer, that heat energy, than what we get back. Does that make sense? It's generated some additional heat energy, which has drifted off into the universe and increased the randomness on a net scale, right? Sure, I've taken this little bit of water and made it more organized, but in the process, I've taken a corresponding other part of the universe, plus a little additional, and made it less organized. The sad reality of this is that unless the universe somehow does something completely unexpected at some point, and reverses its expansion and recontracts, which it's not at all likely to do, based on what we currently know, entropy will continue to increase, and at some point, the energy will be so evenly spread throughout the universe that there won't be enough localized energy to do anything. I mean, there wouldn't even be enough energy for a person to have a thought, for example. The universe died, it's called a heat death. Everything just becomes cold and lifeless and free. Now, I'm talking about, you know, trillions and trillions and trillions of years in the future, so it's nothing to worry about, but that's where this eventually goes. That's sort of the end game. But so the point is, though, this whole thing then is that within a closed system, we could say energy is conserved, right? Okay, so then it ought to be easy for us to say, okay, so this pen right now has a certain energy, and now it has a certain different energy, right? What's its energy? Right there. Not much? Not that much, probably, right? Okay. What do you think, estimate in grams? Anybody good at this? What's estimate the mass of that? Sure, I'll tell you what, I'll give you something to compare it to. I've got, here, this all, what is this? Doesn't have to be exact, but let's just get, here's a 100 grams compared to that pen. Just give me an estimate. 20 grams, I think the pen's 20. Okay, 20 grams. So we'll say this pen has a mass of 20 grams. Let's take a look and let's see how much energy it really does contain. And that's a weird concept, how much energy it contains, right? Does the pen ever really change from being a pen to something else? Not really. We throw stuff away and maybe it biodegrades and turns into other chemicals, but it doesn't change appreciably. When I mean appreciably, its mass doesn't change very much. Okay? We never really talk about the total energy of an object because it's so ridiculous. We always talk about changes in energy. But let's just do this one time. Let's find out how much energy is in this pen. Let's just see, let's think of it in terms of something realistic. Let's take like how much does just a normal car? Probably like, I mean, I don't know, like a 2,000 pounds or so, about a ton, let's say. So that maybe that's a smallish car, but you know, Honda Accord or something, Honda Civic, right? How far, if we extracted this energy, how far do you think I could pick up a Honda, a 1-ton car? Let's just see. If we took all the work out of this, all the energy, converted it perfectly efficiently into work. Let's see. Okay, so Einstein will help us out here. Einstein is the person who first realized that energy and mass are equivalent. That the total amount of energy stored in something is actually given to us by that equation, where C is the speed of light. Okay? So he said 20 grams, right?
Yeah.
So that's 20,000th of a kilogram. Not very much. Right, so let's calculate this. Okay, standard units, that's what we get. So that's big. Okay. Maybe a lot bigger than we thought it was.
Is it potential energy?
This is, in a sense, yeah. This is just the total energy stored in the mass of this pen. So in other words, if this mass were to be completely converted into energy, how much energy is actually stored in this pen? And then we'll talk about how far we'll get with this today, but we'll wrap this up by talking about how maybe this is just sort of an academic argument. And so, all right, so let's figure this one out. First of all, so we get 0.2 times, oh, 0.2, whoops. 0.2 times 3 e to the 8 squared. Okay, we get a big number. 1.8 times 10 to the 50 joules. Okay. Okay, let's figure out the amount of work required to pick that car up. Well, let's say the car was a little bit heavier. Let's say it's about 2,200 pounds. So it has a mass of about 1,000 kilograms. Okay? So this is going to be equal to, and I'm going to call n the number of cars that we could pick up 1 meter. How about with this? Okay? So n times 1,000 kilograms times g times 1 meter, because that's the amount of work required to pick up a 1,000 kilogram car, 1 meter, isn't it?
And then
1,000 times roughly 10, so about 10,000 newtons times 1 meter, about 10,000 joules. Okay, well, so we'll just divide this by 10,000. And the answer is 1.8 times 10 to the 11. Yeah, it's a lot. Okay, how many people are there on Earth?
Like,
About 7
7
billion-ish, about 7 billion. So let's see how many cars per person could be picked up 1 meter by the energy stored in this pen. So divided by 7, 1, 2, 3, 1, 2, 3, 1, 2, 3 equals, oh, that's not bad. Not quite 26 cars per person for every man, woman, and child on Earth, 1 meter of the energy stored in this little pen. That's a lot of energy, right? Fortunately for us, the energy tends to stay in the pen. But in instances where energy doesn't stay like it's supposed to, if it's well behaved, it doesn't stay as mass, what happens? Yeah, well, you get things like an atom bomb, right? And that's really what an atom bomb does. All an atom bomb does is, via a nuclear reaction, it just converts some small percentage of the mass of the uranium or plutonium into energy, and most of it just degrades into some other, it goes through decay process and turns into some other element. A very, very small percentage of it is converted into energy, and look what you get. Right? So you kind of get an idea that, talking about absolute energy is a little bit ridiculous, because almost never do we do that. Now, it does happen. If you were to, for example, very accurately weigh a piece of dry wood and all of the oxygen that is used up when it's burned, and gathered up all the smoke and the ash, you would find that there is a small difference in the mass before and after. There has to be, because a bunch of energy was liberated, right? It created a lot of energy and a lot of heat energy. And so some little bit is lost. How much is lost? Well, that much is lost. That much is lost, according to that equation. Okay? So, anyway, we don't really need to worry about absolute energy, though, in circumstances like we've talked about. All we really need to worry about are changes in energy, right? Okay, so when we go back to something like this, this situation, well, that's easy to deal with, right? We don't need to know what the absolute energy is. We just need to know what the changes in energy are. And so to do that, we're just going to define some reference point that we're going to call h equals 0. And we'll make it a convenient one. Like if we were launching objects off the floor, we'd probably pick the floor, right, as h equals 0. Arbitrary. Doesn't matter, right? But we just got to pick some place so we can be consistent. When we do that, we're just, all we're doing is we're setting some arbitrary standard, because in reality, the total amount of energy in that object is astronomically large, right? Make sense? Okay. I mean, we could define it relative to Alpha Centauri or something, some other star. Not very convenient, but it would still work. Right? Right? Questions? Does that make sense? Are we getting close to the, did I get this about right? 10 minutes? All right. Yeah.
So, where does the energy come from when you use fission?
When you use fusion? Okay, good question. So where does the energy come from? Very good question. So where does all that energy come from when you, let's say you use fission, for example, when you explode an atomic bomb? Where does it come from? Where does it come from? Yeah, okay, but how do they get stored there? It gets stored there in a supernova. It gets stored there, yeah, that's how it gets stored there. So all the uranium and plutonium that exists in the universe, in fact, all of the iron, all of the nickel, all of the heavier elements that exist in the universe come from supernova. Okay. And the reason that is because only in those situations is the local energy state high enough to compress atoms so much that they'll actually stick together in a stable state. So you get this enormous explosion where and it's just a very, very tiny percentage of the mass of the star is converted into these heavy elements. Most of it just gets blown out of the universe's hydrogen. But, you know, there's a little tiny bit, but it's massive, and so it's gravitationally attracted, and so the dust, it's just in the form of dust and particles. Eventually, this stuff just moves through space and comes into the vicinity of a forming star or an existent star, and it's gravitationally harnessed, and it kind of comes together, gloms together, and you form rocky planets. It's just being built from all this dust that's been created by supernova.
Is that like the Big Earth? Or
Yeah, like the Earth, exactly. So all the uranium that we mine out of the Earth was created in some big supernova, or multiple supernovas. In fact, almost everything you're made of is literally stardust. It's all stuff that comes from a supernova. Yeah, literally. Yeah. So that's where it comes from. So you're exploiting the favor the universe did for you when it created those materials, not the favor in that case. And then same thing with fusion. With fusion, there's a certain amount of energy that is stored in terms of just the structure of the hydrogen atoms, so that when the hydrogen atoms come together and fuse and form helium, that's a lower energy state, and so some energy is released in the process. Now, you have to get it over this big energy hump, and this is kind of interesting. The way you would describe this, it sits in an energy well. So, here's what you get. Here's how you could visualize this. And I want you to notice that the reason that I have hammered mechanics so much is that every model, when we're talking about stuff like this, we use mechanical models. When we want to talk about how it is that fusion works, we just look in a two-dimensional space where we've got energy, I want to represent this. So we've got well, I don't know how I'm going to label this. It's going to make sense. Let's just do it like this. Something like that. Okay, so we've got, this is energy, and so we have to, if we can, it's like we have a ball on a landscape. That represents the energy state of the energy that's stored in the materials that we're going to fuse to create a fusion reaction. Okay, so they're sitting here relative. Hydrogen is stable by itself, right?
Yeah, very
But if I compress hydrogen enough, if I compress it enough and I invest enough energy in it, I can make this ball rock around in this little divot on the hillside. If I can give it enough energy to get up over the edge of that hump, then it's going to fall clear down the mountainside and release all of the energy that it had stored previously, right? But it's pretty stable. I got to be able to push it over that hump first to be able to release all that energy, right? And so that's the cost associated with fusion. You got to be able to generate these huge temperatures and pressures to push it over that hump, and then it releases all the stored energy, right? And nuclear potential energy. Nuclear.
Is a catalyst what lowers that energy number? That
Say it again.
like a catalyst, that's what lowers that.
So what a catalyst does, is a catalyst can do one of two things. A catalyst, you could be seen as something that's going to push this up, or it's going to lower this hump. Okay? Yeah. It expedites the reaction. No. No, the only catalyst, like if you're talking about a fission bomb, the only thing that matters is critical mass, right? Because what's happening in a fission bomb is, as the fissile material, like plutonium, let's just say, as that decays, it shoots off little neutrons, right? And when the neutrons hit adjoining atoms, they liberate other neutrons, right?
And so they just keep liberating.
Right, and so if the pieces are far enough apart, what we call the flux of neutrons, the sort of the density of neutrons that are going to hit the target goes down, right? most of them spray out in other places. But when I put the two pieces of fissile material close together, then the flux goes up. If I put them right next to each other, then, half the neutrons go this way, but half of them get embedded in this other piece of plutonium. And before you know it, then you've got a runaway train, right? It's called when it goes supercritical, there's no turning back. At that point, there's enough neutrons swimming around in the materials that it's going to explode. So all you have to do, if you guys want to build an atomic bomb, I can tell you how to do it. It's really not that hard. All you got to do is get. Yeah, I'm recording. Yeah. All you got to do is just get two pieces of plutonium, maybe shaped like hemispheres, put them at the opposite ends of this big cylinder, and explode them with such spectacular timing that they fly together in the exact middle, and they weld together because they're shot, it's metal, and they're shot so hard that they just sort of deform and weld together, plus they get real hot. Okay, but the problem with that is that plutonium is hard to get. It's the most well accounted for material on the face of the earth. Plutonium is one of the very few things where you lose due process. If you are suspected of having plutonium, you can be shot. I mean, it's not even like you have to have due process in that case. It's something, yeah, because it's such a national security risk. So yeah, so it's not something. I feel pretty safe giving you the instructions for building an atomic bomb. Plus, I didn't really give you the instructions. There's a little more to it than that. But essentially, that's all it is you're taking two subcritical masses and you're putting them together so they become supercritical.
What about uranium?
Okay, so it would work with U-238. Has to be enriched uranium. Yeah. Question?
I've heard in a few different places, like a boy who was playing around with some nuclear material, and he was like gathering fire alarms, like smoke detectors.
Mm-hmm.
So he was just like stripping those, and then like furnace was gonna be bigger than that.
No, but boy, it's a pretty dumb idea because you're gonna get. I mean, you become exposed to. Well, there's no plutonium, just other radioactive. Nothing that could ever explode. But not a real good idea. I mean, anytime you're near any concentration of radio, and this is hard radiation. This is, that's not a good idea.
You didn't look too good to smoke shot.
No. No, he's likely to get cancer.